Hello, this is Chapter 1, which is the review of general chemistry. We'll talk about electrons, bonds, and molecular properties. Before we get to that, I just want to talk about what organic chemistry is. So formerly, the definition of organic chemistry was the study of compounds that came from natural plants and animals. But now it has expanded to the study of carbon-containing molecules and the reactions that they undergo. So we'll look at how molecules collide and how bonds are broken and bonds are made to make new molecules. So who cares about all of these organic chemistry molecules? Well, we should care because the food is made of carbon, drinks are made from carbon molecules, our clothing, pharmaceuticals, so medications that are synthesized in the lab, those are made using organic reactions or molecules, pesticides, paints. If you've ever used a Post-it, that adhesive is made using polymer chemistry, which is a branch of organic chemistry. Also, the DNA and RNA and protein synthesis in our bodies are coming from organic molecules, and also plastic. So Kevlar, polyester, polyethylene, those are all organic molecules. So we start with two compounds we see here. So both of these have the formula C2H6O. So you can count those up, the carbons and the hydrogens on each of them. But if you notice, they both have different names. One is called dimethyl ether, the other is called ethanol. They have different properties. So the boiling point of one is negative 23 degrees Celsius, while the other is 78.4 degrees Celsius. One thing that you'll notice is that they're connected differently. So here the oxygen is sandwiched between the two carbons, and here it's hanging out on the end. So these two compounds are constitutional isomers of each other, which means that they're compounds with the same molecular formula. They have different physical properties and different names. So they're same molecular formula, different properties. I'm going to add here different connectivity. So the oxygens again are differently connected to the carbons. So if we look at these four structures down here, this OH group is bonded to carbon number 1. This OH group is bonded to carbon number 1. It hasn't been changed physically, it's just in a different orientation. So it's kind of like if you had your arm sticking straight out here and then you move it to straight up over your head. You haven't connected your arm differently, so those two compounds are the same thing. Here you can take that same arm and wave it down by your side, and that is the same isomer. We haven't moved anything. Here, if you turn around and you stick that arm up to the side, that's the same thing as well. So all of these are the same molecules. These are not constitutional isomers. So they have the same molecular formula, but their connectivity is the same in all of them, so that makes them not a constitutional isomer. So when we look at different molecules, in organic chemistry, we only focus on a small part of the periodic table. So in general chemistry, you had to learn all about all the atoms really, or at least a lot of them. This is just a small chunk. So if you can remember how many bonds carbon makes, nitrogen, oxygen, hydrogen, and the halides, you should be at an okay spot for yourself in organic chemistry. So carbon is tetravalent, which means that it forms 4 bonds. Nitrogen is trivalent, it forms 3 bonds generally. Oxygen is divalent, it forms 2 bonds. Sometimes we will look at sulfur, which is just under oxygen in the periodic table, and it does the same thing, it forms 2 bonds. Monovalent compounds like hydrogen or the halogens form only 1 bond. So these are the atoms that are commonly bonded to carbon. So the nitrogen, oxygen, hydrogen, and the halogens. So we have a practice problem here. When we get to practice problems, I usually encourage you to pause the video and try to do the problem yourself, but you can certainly watch me do the solution for the first one and then try the other two. This one only has one. So we're going to draw constitutional isomers for a molecule with the formula C3H8. So the first thing you want to do is remember that the definition of a constitutional isomer has the same molecular formula. It's connected differently. We're going to look at one thing here. So we want to remember carbon makes 4 bonds. Hydrogen makes 1. And oxygen forms 2 bonds. So we want to fit these things together so that everybody has a full octet or hydrogen has its 1 bond. So the first one I'm going to draw, I'm just going to do the carbons straight across. Hydrogen here, and I'm going to put the OH or an OH on the end here. So we have 3 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen. So this is one isomer of that formula. So to draw the next one, my compound has to be connected differently. So if you built a structure out of Legos and you turned it around flipped it over, that's going to be the same structure. It's not going to be something different unless you physically take a piece off and connect it somewhere else. So I'm going to take this OH group and connect it somewhere else. So here it's on the first carbon, which is really the same as the third carbon if you flip it over, but I'm going to put it on the second carbon, and that's going to make it a different molecule. So that would be a different constitutional isomer. So I physically taken the OH off, disconnected it, and switched it with this hydrogen over here. So now the OH is on the second carbon. That's a different isomer. One other one that you can make is sandwiching the oxygen between two carbons. So now the oxygen makes two bonds. That one's happy. We just have to fill in hydrogens everywhere else. So that would be the three constitutional isomers of C3H8. Oh, so now that you've been drawing bonds, we can define what a bond is. For organic chemistry, we're going to look at covalent bonds, and that is the bond between two atoms that are formed by sharing electrons, and that's to fulfill their full octet. They want to have full octet, or in the case of hydrogen, have its 2 electrons. So here we have hydrogen and hydrogen. Those 2 electrons get together, and they form one covalent bond. So if you remember from general chemistry, a proton has a positive charge, neutrons have no charge, and electrons are outside of the nucleus and those have a negative charge. And they often will move to minimize repulsive charges. So the first shell will hold 2s electrons, and the second shell has that full octet. That's the p shell. So this is the s shell, if you remember that. This is the p shell. Electrons that are in the outermost shell are the valence electrons, and that is determined by the group number. So for a 7A, those have 7 valence electrons. 6A have 6, 5, 4, and 3. So that's the number of valence electrons. And the Lewis dot structure will represent these valence electrons. So if you were drawing the Lewis dot structure for chlorine, you wouldn't include the 1s2, 2s2, 2p6. You would just have the 3s2 part of it. That is the valence electron part of it. For the rules for drawing Lewis structures, you want to first draw all the individual atoms with their valence electrons, and then connect them so that they can form more than one bond if needed, or connect the hydrogen atoms because those only make one bond, and then pair up any unpaired electrons so that they get an octet. So sometimes this requires using a double bond or a triple bond. Okay, so if we're drawing the Lewis structure of CH2O, we have a carbon, our oxygen with the 6 valence electrons, and 2 hydrogens. We can start putting the pieces together. So if I went O, H. All right, so hydrogen has its 2 electrons. Oxygen has 2, 4, 6, 8. Carbon, I can put 1 hydrogen here. But carbon still has these 2 unpaired electrons, and I already have used up my atoms. So I need to think about a different one. So if I put carbon, oxygen, that's the one left over here. There's 2 hydrogens. I have 1 extra electron. So carbon has 2, 4, 6, 7. Oxygen has 2, 4, 6, 7. So what you can do is join those 2 together to form a new bond. So we have carbon double bond oxygen. Hydrogen's happy. Carbon now has 8 electrons. Oxygen has 8 electrons. So that's how we would draw that. So again, here's a couple of practice problems. You might want to take a minute to try and do the problems before looking at the solutions here. So for C3H6, once you start drawing them out, you'll soon realize that I'm going to have a double bond somewhere because you have electrons left over. So I have this hydrogen is going to be C2, double bond here. So we have C3H1, 2, 3, 4, 5, 6. Sometimes the molecules are written out in a way that you can tell how they're connected. So these C's are connected together, and then the oxygen's on the end. And that's an OH. This is a CH2, CH3. And then one thing that you want to be careful of when you're drawing Lewis structures is you have to draw in the electron lone pairs for those. For here, we have CH3. That's bonded to a carbon with the nitrogen. Carbon's got 2 left over, so those get together, those get together. And then we get a carbon that's triple bonded to a nitrogen. So again, nitrogen has the lone pair, and it's making 3 bonds, which nitrogen likes to do. Carbon has 4 bonds. Everybody's happy there. When you have unhappy atoms, that happens to have a charge associated with it because it doesn't have the right number of valence electrons. And when that happens, that's known as formal charge. And to calculate that, it's the number of valence electrons of an atom minus the number of bonds minus the number of non-bonding electrons here. The E minus. I will sometimes use E minus to represent electrons. Not sometimes. Most times I'll use E minus. So to find the number of valence electrons first, carbon, again, that's in row 4. So for carbon that has 4 valence electrons, determine the actual valence. So how many bonds is it actually making? It's making 4 bonds. There's no non-bonding electron pairs, so this is 0. For nitrogen, that has 5 valence. It's making 4 bonds. There's no non-bonding electron pairs, so this is 1. That one's going to be plus. Okay, so why don't you go ahead and try to do these ones. Oxygen has 6 valence. It's making 3 bonds and has 2 electron lone pairs. So 6 minus 3 minus 2 is plus 1. That is the charge on oxygen. For carbon, we have 4 minus 4. Nitrogen is 5 minus 2 minus 4. And we get minus 1. And then carbon is 4 minus 4, which is 0. All right, some other types of bonds we might encounter are ionic bonds, although these are not that important for organic chemistry. This occurs when you have a bond between 2 atoms that have electrostatic attraction between them with opposite charges. So an example of that would be sodium chloride or a table salt. So those have the opposite charges, those are attracted together, but it's not a covalent bond. Covalent bonds, again, are sharing of electrons in order to fulfill both outer shells. And then you can have also a polar covalent bond, which is a covalent bond that happens when electrons are not equally shared between atoms. And this occurs if you have 2 atoms bonded together that have differing electronegativities. So hydrogen is not electronegative, carbon is not that much either. There's a small difference there. But between carbon and fluorine, there's a greater difference. So this is the most electronegative atom. That increases as you move from left to right and up on the periodic table. And the bonding electrons are more attracted to the atom with the higher electronegativity. So if you had a carbon bonded to fluorine, most of the electron density is here. All right, so again, most of the electron density is on the more electronegative atom. Okay, so if we look at chloromethane, carbon is electropositive, chlorine is electronegative, so you can see that's represented by these partial charges. And then this dipole arrow represents the direction of electron density. So this is where the negative part is, the arrowhead, and then the tail here where this plus, that's where the positive is. We can also see it in electrostatic potential maps with chloromethane. So you have a carbon that's positive, this area is the negative portion of it, and then this again is just the color scale. So you can see blue is the most positive, red is the most negative part. When we're looking at polar covalent bonds, we can show the partial charges. So an example here is methanol. To identify all the charges, carbon to oxygen moves that way because oxygen's more electronegative. Hydrogen to oxygen, that's more electronegative here. So I'm going to put the partial negative, and our partial positives are over here. So you can try to do the next problems, and you'd have a lot of arrows here. There's not an overall one, you'd have individual ones. So again, oxygen to carbon. And then to carbon to fluorine. For these next couple sections with the atomic orbitals, I'm not going to ask you specific nitty-gritty questions about them. So if the mention of atomic orbitals is stressing you out, just take it down a notch. This is just kind of review so you can know it's there. But again, I'm not going to ask you specific questions on this on quizzes or exams. Quantum mechanics is used to explain wave properties of electrons. In an orbital, there's a 90% probability of being able to find an electron in there. As you get farther away from the nucleus, that probability goes down. So the orbital regions can be in the negative, positive, or zero area, and the sign of the wave function has nothing to do with the electrical charge. So even though there's a positive charge here, there's still a probability of finding an electron. In this p orbital, this is the p orbital, you can find a node, and a node is the 0% chance of finding an electron. Electrons are filled using 3 rules. The first is the off-ball principle, and that is where the lowest energy orbital is filled first. So the 1s's are going to get filled before the 2p's. And the Pauli exclusion principle tells us that each orbital is going to have 2 electrons with opposite spin, so you won't see an orbital with spin in the same direction. And then Hund's rule, when it has degenerate orbitals, put them in singly before you pair them up. So with carbon, there's 2 electrons here. You wouldn't have filled it up like this and then left 2 blank ones. So that's not the way to do that. So with boron, the electron configuration is 1s2, 2s2, 2p1. So there's that 1p there. Carbon is the same, 1s2, 2s2. This is 2p2. For nitrogen, you would fill it 1s2, 2s2. This one's 3p3. So again, we're going to put 1 electron in each orbital instead of doubling up the 2 there. Oxygen has the 2p4. Okay, I put that one there because I knew that was the 4, but that's how you would do all 3 first and then come back and do that one. So for fluorine, that's 2p5, so 1, 2, 3, 4, 5. So that's how we would fill those electrons. So a bond occurs when atomic orbitals overlap. So overlapping orbitals are kind of like overlapping waves. So if you have 2 electrons separately coming from different waves, and you bring those waves closer together, that closes in their internuclear distance, and those waves reinforce each other and get bigger and form constructive interference, which produces a larger amplitude wave. But if you have waves that are in opposite directions and you bring those out, those cancel each other out. That forms a node and gets you destructive interference. So that results in canceling waves and it produces a node. So then we have valence bond theory, which is simply the sharing of electron density between 2 atoms, and that results from the constructive interference of those 2 waves that we talked about getting together. So we have hydrogen, hydrogen, those 2 electrons come together to form that bond, and we get this circular cross section. So the bond for an H2 molecule results from constructive interference. So again, these last couple slides, they're not going to be super specific questions on atomic orbitals or valence bond theory.